Hello, everyone. Welcome to another webinar. My name is Javier, and I'm here with my colleague Manu. We will talk about real-time fraud detection and how we can leverage rolling aggregations at the scale to make a more accurate detection of fraudulent transactions. So, as you may already know, there was this research from Google where they were studying the different latencies when users were interacting with the system, and they were basically investigating how much latency will mean less less responsiveness of the system, or if users are actually losing track of the activity in the system. And they basically realized that more or less the threshold would be like 200 milliseconds when if the requests are slower than that, the responses are slower than that, then you might have an impact on user experience actually. But speed, in the end, it matters not only in reactive system or interactive systems, but also when it comes to making real-time decisions. If you have contextual information of the latest state or the latest events, you might be able to make basically more accurate or precise decisions. So that it also matters for this type of cases. And basically, we can say that when building machine learning systems that provide a value to our businesses, if you are building a system that deals with data that is closer to real time, it would mean that you will enable more value basically out of this system. So we can differentiate between like different categories, like if the system uses static data or batch data or a bit closer to real time. And when we refer to real time, basically what we are meaning here in this case is we're talking about feature freshness, which basically means how fresh are our features. So since the time I'm receiving events, there is imagine that there is a data stream. So I have events coming in, and then I'm computing aggregates, or I'm extracting features out of these data streams. The time it takes for these features or computations to be available to make decisions, this time is basically referred to as feature freshness. And we talked a lot about real time, but in the end, like not everything is the same kind of real time. So we have, as for some cases, we may be okay if the values, if the latest values of the information of the context that we have to make decisions is not that much updated, or in other cases it's crucial to actually make decisions on the latest value. So in the end, how fresh is our data will depend on different decisions on the architecture level, and which processing engines are we using, and how are we actually computing these features in a streaming manner, and some other things that we will see later on. So if we are talking about feature freshness, we need to explain we need to have clear why is actually feature freshness important. And for example, if we take into account use case of detecting fraud from credit card transactions, we can see that, for example, at the right hand, we have this AI-enabled system that users will interact with, and when trying to buy something, to make a transaction, then information of this, IDs of this user and the credit card number will be sent to our system that will try to predict if it's a fraudulent transaction or not. And this fraud detector, as we can call it, will use these IDs to retrieve some context and history related to this user and the credit card activity, and then trying to figure out if it's a fraud or not. And the thing is that this context and history that the fraud detector will use is updated over time. So we will have like this real-time data processing, or like a streaming pipeline that is receiving and processing events as they happen when the user, for example, logs into the service, or makes a new transaction or some other operations. These events will be processed in our streaming pipeline and will add to this context that will be used later on for the predictions. So basically, the more updated this context is, the more accurate predictions or classification of these transactions we can achieve. So that's why feature freshness is more important to in some cases than others. So when it comes to computing these features in our system, we can kind of simplify it in a little bit in using this diagram. We will have, we see on the left, we have some different sources where data is coming in. We can have a stream source or a batch source, maybe like where we basically compute, we process this raw data coming in, and we extract our features and compute meaningful features that then later on we will store in our feature store. And on the other hand, we have our predictor or our fraud detector that is running on an internet pipeline. And as requests come in, this model deployment will fetch or retrieve these feature vectors, the pre-computed features that were computed on the feature pipelines on the left. And possibly it can also, depending on the data transformations to compute the features, it might need to compute some features directly on the model deployment. So basically, the feature computation can happen either before writing to the store, the feature store, or also at prediction time based on some request parameters that can be sent from the service. So when we talk about a feature computation before writing to the feature store, we normally mean shift left computation, because it's like we are trying to shift to the left computation of features, and basically prevent any computation from happening later on at prediction time, which might add some latency. And basically, this is these features we tend to refer to them as pre-computed features. And then if we look at the features that are computed on demand at prediction time using the request parameters, we can, on the contrary, refer to these computations as shift right computations. And there is no one fit all solution in this case. So it will depend on your requirements and what type of computation or feature computation you want to perform, and so on. But in general, if you try to shift the computation of features to the left, it will mean that you have to set up some. So you have to consider in your architecture some streaming processing engine, and you might need to depending on the processing engine that you are using, you may need to figure out how to integrate it with the rest of the platform, and so on. So in terms of infrastructure, it may add complexity. But then when it comes to retrieving these pre-computed features, it will mean lower latencies, because our fraud detector or the model deployment will just fetch these features that are already pre-computed using the private keys or the IDs of the user and credit card transaction, credit card number, and so on. And related to the safe drive computation, if you try to basically sift to the right the computation of features, you can see you can leverage like less or lower lower complexity in terms of infrastructure, because you may be able to get rid of streaming processing engines if the computations are simple enough, and also if you have all the information that you need to compute the features. So if all the information comes in the request, then you may be able to run this feature computation on the right, and then get rid of the stream processing engine. So this will mean basically less complexity in the infrastructure, but it can, on the contrary, add more latencies when it comes to the responses that we will send back to the AI-enabled service. So if we have to run the computations at prediction time, the computations are or the transformations are a bit more complex, or it takes more time, it will add latencies for the final response. So in this case, we will focus a little bit more on the streaming feature pipelines and how to try, and we will see how different types of feature computations using different Windows techniques, and especially the rolling aggregations, will or can lead to or can have an impact on a lower feature freshness. So just as a quick recap on data streams, as we know, data streams are continuous, unbounded data flows or flows of data. And when you process data streams, you normally use windowing techniques to basically segment your data and perform some transformations on these windows. And these transformations can be stateless or can be stateful. And depending on the windows and the transformations that you do, basically you can get aggregations computed on like, okay, is real time or near real time, or actually immediate computations, as we will see later. And some examples of these stateless and stateful data transformations are, as you know, like if we just want to discard some events or to filter these events, or perform some type of mapping between the event that is coming in and the result that will be as output. This will basically not rely or not need any internal state related to the previous computations that were performed with previous events. So you don't need any information about the past. You can just compute the transformation as it is with the coming events. And then for the stateful transformations, you normally keep some state related to the already processed events. And this can be seen in typically in window aggregations or session-based aggregations. We will see later, and so on. So when implementing a feature, when basically building systems that compute that integrates streaming feature pipelines to compute features over time on raw data coming from data streams, you have different engines and platforms that you can use, and it basically will depend on how does your data look like, if it's if you're working on big data or smaller data, and also how close to real time you want to be when basically having the latest aggregations ready to be consumed by your models. So we have, as we know, we have different options of engines and platforms like Flink, Spark, and then some others that are a bit more new, like Feldera, or Python-based like Quix, Bytebox, or Pathway. As I mentioned before, basically there are a bunch of criteria that you will need to consider when choosing one of these in terms of how much feature freshness you will need, and also the size of your data. And if we take two of the most popular ones are Spark and Flink, and then also Feldera, which is a bit more recent, but has some specific features that are very interesting for our use case at the moment. We can see that comparing Spark to Flink, both are multi-node. Both can run on a multi-node cluster, while Caldera can it's just a single host engine, and they provide different APIs to basically implement your transformations. As normally as normal, like Python and Java and SQL, while Caldera just focused on declarative SQL in this case. And one of the downsides in this case from Spark is that the way it's implemented, or the way it works, is that it performs micro batching in the events that are coming in. So the processing will the processing will take a bit longer, because it will process all the events in small batches of data, and it cannot be in a continuous manner as new events come in. So you will always have a greater latency when it comes to getting your features ready. And if we compare Flink and Feldera, both support continuous processing of your events, so they can provide under a second of feature freshness. But when it comes to complexity or overhead for the computations, we see that with Flink, every time a new event comes in, the computation or the aggregation in the whole window will happen using all the values within the window, while with Feldera is a bit more, it's quite more efficient, because it leverages incremental views. And this is especially interesting for rolling aggregations, because as we will see later, not all the data in the windows will be used to compute the new aggregations when one event comes in, but instead just the changes in the first and last event will be used to recompute or to update the aggregation. But then, as I mentioned, there are other criteria that you may need to consider when choosing one of these processing engines. So, for example, if you need to use Python, if Python is a requirement, then you may you wouldn't be able to use Feldera in this case. If you care more about lower latencies, you would end up using that's actually wrong. But yeah, if you end up if Python is basically a requirement, you will end up using Bytewax or Pathway or Quix, because they offer lower latencies than PySpark and PyFlink. Yeah. So basically, something that we need to take into account is that the types of windows or the way we configure our window based aggregations determine feature freshness in the end, which is what we are targeting in this session. So we have different type of windows, as you know. We have windows that cover different sessions, and they expire based on an activity of the user or after a period of time. And also we have global windows that basically cover the whole execution of your processing job. So in these cases, it means that when it comes to feature freshness, we will have the aggregations computed after at least the length of the session for in case of the session windows. And in case of the global window, it's basically at the end of the whole processing time, because it's when you finally get the final output. So you normally prefer or you normally end up implementing aggregations that are based on time windows. So we have here different options. We have tumbling windows, which basically they are not so these windows are not overlapping. When one of them finishes, then the other one starts. And in this case, you will get like OKS real-time features, because in the end there will be some delay that we call here evaluation delay, which is basically the length of the window, because until the window closes, you will not compute the aggregation on all the values. So all the events that are coming in before the window closes, those are not being considered yet in your online predictions. And additionally, normally these streaming platforms support what is called watermarks that helps you dealing with events that are delayed. So it's kind of a wait time until you compute the whole aggregation, just in case there's an event that is coming later on. So in that case, the whole the total evaluation delay will basically add up between watermark and the window length. Then we also have hopping or sliding windows, which basically is more or less the same concept, but in this case the window overlaps, so it doesn't necessarily need to finish until the next window will start. And basically the time between one window starts and the next one starts is called the hop size. And in terms of feature freshness, this type of aggregation works a little bit better, because you will get the aggregations are computed more often or sooner, let's say. So you will get like nearer real-time feature freshness. But still, there is some delay, and there are some events that you may miss when making your online predictions. And then there is another type of aggregation, which is the rolling aggregations, that we can think of it as the queen of features for real time, and it basically means no delay in the aggregates. There is no watermark, there is no hop size, there is no waiting time, let's say. And every time an event comes in, then this event is triggered on the recomputation of the window, which can happen um, um, differently depending on the platform that you are running in. So in the case of Flink, for example, the whole aggregation will be recomputed fully every time one event comes in. But for example, if you're using Caldera that supports incremental views, you will every time the aggregation is recomputed, not all the values are used to recompute the aggregation, but only changes between the new one coming in and the state of the previous computation will be taken into account to update the aggregation. So basically, what we can say here is that when using incremental views, you can basically get further features. Incremental views are similar to traditional database views, but basically they are updated incrementally. And as I mentioned, there is no full recomputation using the whole window data, but just the new event coming in is being processed and taken into account for the update of the aggregation. So in the end, it means that when you're using incremental views, the computation of features is more computationally efficient, and also in terms of memory and storage. And in the end, you will get lower latencies, because as soon as the new event comes in, the time that it takes to update the aggregation is much faster than if you compute using all of the values again. And there is yet another approach that has been presented kind of recently as well by Airbnb, that is used in Airbnb crawling framework, which is called tile window aggregation. And in this case, if you consider tumbling windows, instead of waiting until the window finishes to perform the computation, what you can do is to compute aggregations on subsets of events within these windows, and this segmentation is called tiles. So you compute tile aggregations on events within a window. So then when the time comes to make the prediction online, then what you can do is to retrieve these tile aggregations and then combine it with the results of computing the aggregations with the latest data coming from the request features, the request parameters. You combine both, basically, the tile aggregation with the result of the on-demand transformations, and then you will get a bit closer to real time than if you just use tumbling windows, because you are basically adding these tile aggregations to the context. But if we come back to our diagram, our explanation between shift left and right, shift right competition of features, when you're using rolling aggregations, you are basically completely shifting the feature computation to the left, because you will be dealing with you will be using incremental views. That this happens in your streaming feature pipeline. And if you're using tile window aggregations, you will be basically implementing like a mix of shift left and shift right feature computation, because these tile aggregations will happen on the streaming feature pipeline, and then you will also perform some on-demand transformations, and then the results will be combined for making the prediction. So in this case, you may have, depending on your use case, you may have a bit more latencies as well, if you're depending on the type of transformation that you need to perform, and on how much data on the on-demand on the right side of things. And then you also get a little bit higher complexity in terms of infrastructure, because in this case you will need to implement both, like integrate a streaming processing engine in your architecture, and also a solution for computing these on-demand transformations. But as I said before, it normally depends on your use case. So, for example, if your on-demand transformations do not require a lot of information, and all this information comes from the request parameters, and the computation is not complex, then you might get you might just be like okay with performing this feature computation on the on-demand transformations, but so it's a little bit of depends on the use case. So now we will see a demo of how to use HopSworks to build a reactive machine learning system for the fraud detection use case that uses Feldera for the computation of some feature aggregations.
So thank you, Javier, for the session. So like I'll be taking you through a simple demo that uses HopsWorks and integrate and Feldera for creating a streaming pipeline. So by the main idea is to show how you can integrate HopsWorks with Feldera and show how you can have on-demand transmissions along with it. So the whole demo consists mainly of like 3 components. So we have a backfill feature pipeline that ingests some backfill data, historical data, into some feature groups, and has some on-demand transmissions that usually require some request time parameters to be computed. And we have streaming pipelines that are set that reach from Kafka topic. In this case, a simulated transactions Kafka topic created, and that inserts the data using Feldera into HopsWorks. So Feldera, like we have discussed, provides a very efficient way to do rolling aggregations using their incremental views. So we'll see how that is done. And finally, we have the last part, which is the training and inference pipeline that brings all these feature groups that were created, the streaming and the batch feature groups, and performs point in time correct joins to create and applies model dependent transformations if required to create the training data sets and create models that can be deployed in HopsWorks itself. So I'll start showing the demo so we can have a look through the code. Yep. So we'll start by looking at our backfill pipeline that writes historical data to the feature groups inside our feature store. So I have created simulated transactions data in 2 CSV files for the historical transactions data and the KYC files. The historical transaction data consists aggregate of features like set of features like credit card numbers, amount, latitude, longitudes, and the KYC contains mostly user informations. So the first step would be feature engineering, and since this is a backfill pipeline, and most of the aggregations are done in the streaming pipeline. So this pipeline just creates some on-demand features. So in this case, an on-demand feature is usually a feature that requires some sort of request time parameters to be available for them to be computed. So a very naive, a very simple example for an on-demand transformation in the case of on-demand feature in the case of transactions use like a fraud use case would be like a card expires or like the age of the transaction. So in both these cases, the age can only be computed, or the days till the expiry of the credit card can only be computed when the time of the transaction is known. So these computations and can be done in at the time of inference. So HopsWorks provides you capabilities of defining transformation functions using a decorator. You can see an example here. And HopsWorks also allows you to attach these transformation functions into a feature group while creating it, and that gives you an on-demand transformation. So like by default, on-demand transformations are applied when you ingest data into a feature group, as well as when you try to read data for online inference. So this gives you a lot of you don't have code duplications, and you have more consistency in your code. So we have like 2 small examples of transformation functions here. So we compute the age using the birth date feature and the date time, that is the transaction time of that time of the transaction. So you can just have a quick look forward and see how we create feature groups using that and attach the transformation functions to the feature groups. So you can see that we have created a profiles feature group that contains user data, and we have attached the transaction time, like the age and the credit card expiry days feature transformation functions to it. So these transformation functions are automatically applied when you ingest data into the feature groups using ingest data into the feature groups. So the on-demand features would be on-demand transformations functions would create on-demand features that would that you can usually use as normal features in the feature group itself. So once you insert the feature, you can see them in the UI too. So you can see the transformation. You can see the on-demand features, on-demand feature created by the on-demand transformation function as normal features, and this can be used while creating feature views too. So similarly, two more feature groups are created to backfill historical data. So these are the transaction feature view and fraud labels feature view. The fraud label feature view contains labels that are already known if about if a transaction is a fraudulent transaction or not. So this is a quick walkthrough of uh, the backfill, or let's say the batch pipelines that we have. The data like user data or like user data does not really change frequently and can be handled as a batch pipeline. So now let's have a look at the streaming pipelines that we have. So how this notebook looks through how you can use Feldera to perform aggregated operations and insert data into materialize data into OpsWorks. So for that, first the first step that you would have to do would be creating feature groups with the required feature names. So a little bit of care should be taken to make sure that the schema of a created feature group matches the schema of the data that you returned from Feldera 2. So the first step is creating feature groups, and if you notice, we don't insert data directly into the feature group, but we save the feature group. The save function basically creates metadata, materialize the feature group in OpsWorks with just the metadata. And by default, when a streaming data is inserted into a feature group, we insert it using Kafka. Insert it using Kafka, and that Kafka doesn't really directly write to the offline feature store. So we have to manually call materialization jobs to trigger writing of data from Kafka, or that is the online stream, into the offline feature store. So you can OpsWorks also supports cron jobs to manually materialize trigger offline materialization jobs. So the first step is creating the required feature groups. Here we have created two feature groups to store Window hopping Window aggregations and rolling Window aggregations. We have also selected the transaction feature group that we have backfilled into, fetch the transaction feature group we have backfilled into, so that we can store any newly created transaction streams. So the next step would be connecting to Feldera. You can create a free account in Feldera by going into this tryfeldera.com link. And once you create an account there, you can manually create API keys that can be used to connect to Feldera. And the API keys are HopsWorks provides secrets to store API keys. and you can create a secret that stores your Feldera secret, and that can be fetched by using the secrets API, and you can log into Feldera. Once you log into Feldera, to communicate between Feldera and Hopsworks, you need to provide the Kafka credentials that is used inside Hopsworks. So for that, we use the Kafka API. And you have to also provide the certificates, certificates that you use to provide authentication for external services to communicate with Hopsworks. So that would be the next step that you would do. And finally, then you have to create some configurations, Kafka configurations that needs to be provided, that needs to be given to SQL query that is run inside Feldera, so that the Feldera can read from Hopsworks or write into Hopsworks. So for this demo, we have created a transaction stream that is leveraging Hopsworks internal Kafka, and the simulator's transaction stream is read into Feldera, and then aggregations are performed on it, and then written back to Hopsworks. So you can see how that is done. So the next step would be configuring the source and the sink for Feldera. So the source would be the Kafka topic that creates a simulated stream inside Hopsworks, and the sinks would be the Kafka topics that write to each of the individual feature groups. So we have created 3 feature groups. So we would have to create sync configs for each of the three feature groups. So the sync configs follow a specific syntax that is used. So we have to add the Kafka Kafka configurations along with the feature group name, and we have to specify the schema for the feature group. So the next step is basically creating all this sync configs and source configs. The source config is the simulator stream that we have. So after that, we move on to once you have created all the configurations that you need, you can create the SQL query that does that performs the Feldera aggregations inside Feldera. So the first step is registering the source. We create so basically we create a table inside Feldera that uses our Kafka topic as a connector, and using that table we can create aggregation table. So the first table that is created writes to the transactions feature group, and it performs it just writes the raw feature data into from the simulated transaction stream into a feature group in Hopsworks. The second query basically creates a hopping window aggregation. So we create the hopping window aggregation that has a slide of 1 minute and has a window size of 2 minutes, and that is written into another feature group that has the credit card hopping window aggregates. Similarly, we also have aggregations done for rolling windows. So all this SQL statements, queries can be wrapped into a single pipeline that can be built and executed inside Feldera. So you can use the SQL query generated to build a pipeline, and the pipeline is created inside Feldera, and this automatically reads the data from the source stream and syncs the data back into each of our feature groups when any new event is obtained. And after that, the offline materialization jobs that has been scheduled run periodically to fetch all the data from the online from Kafka and write it to the offline store. So now we have feature groups that use batch data, batch feature pipelines that have like a few online on-demand features on them, and then we have a few streaming feature pipelines that use that have been created using Feldra. Now we can use all these pipelines to create a feature view that can be used to train a model. So we have the aggregated features and we have the batch features. So this can be, we can create, once you have the feature views, feature groups, the feature groups can be created, used to create queries, and the query can be used to create a feature view. Feature view is nothing but a logical representation of a feature, of a collection of feature groups that are joined together by a primary key and an event time. And all the joins inside hopsocks are point in time correct joins too. So we make sure that the joins are point in time correct. Like on-demand features that were attached to on-demand transformation functions that were attached to feature groups, feature views also support attaching transformation functions to it. So transformation functions attached to that are called model-dependent transformations, and usually are transformation functions required for a model. Some examples are label encoder and like simple imputer. So we you can attach any required model dependent transformation functions to it to create the feature view. And the feature view, you like I mentioned before, like the on-demand functions created by in a feature group can be used as normal features in the feature view. So they can, so when a feature vector is read during online inference, you can manually you can recompute the feature on-demand features at that point using any request parameters that is obtained. So this feature view, the fraud feature view, has on-demand functions also included in it. Now, so once a feature view is created, you can create train test split. You can create a training data, and then the training data can be used to train a model, and that can be deployed inside Hopsworks. Once a model is deployed saved inside Hopsworks, once a model is saved inside a model registry in Hopsworks, you can deploy the model. Yeah, so Hopsworks provides for Python model deployments. Hopsworks provides the ability to use predictor scripts. So a predictor script is nothing but a script that you can use to load your model, and then to perform a set of steps before passing it to your model for predictions. So one common thing that you can do inside a predictor is fetching feature vectors. So once you have an input that is required to be and that is a prediction request. When you have a prediction request, you can pass in the prediction request to a deployment, and that internally calls the predict function. And the predict function, you can fetch feature vectors, and here you can pass in any request parameters that you have, like for example the event time or the date time that the transaction is happening, and that can be used to recompute on-demand features. And so this the on-demand features are recomputed here based on the request parameters passed here, and request parameters passed to it. And so we can see that once the model is deployed, you can make predictions on it by passing in the the primary key or the 7 keys and any other request parameters that you need along with it. So once the prediction is so this prediction the deployment internally, like we have seen, fetches the feature vectors and recomputes any on-demand transformations. And here, since we have a streaming pipeline, the streaming pipeline the streaming feature groups always updates the events or always has the latest events updated. And you can see that here in this. I can show you a small demo in which we create a new we publish a new transaction event, and you can see that it is get the features are you can see that it is received in Fildera, and Fildera writes it, and you can and the feature and the deployment gets the new features. So if I publish one more event to Fildera, then you can to the simulated event source, you can see that you get a new yeah, you get a new event, new feature, a new value for the feature vector for the exact same value for credit card. So like the feature values are updated very quickly from Fildera. Yeah, so that would be a quick demo on how you can integrate.
So if you want to learn more about running aggregations and how to build basically a real-time or reactive machine learning systems, you can also scan this QR code to download the first chapter of a book that our CEO Tim Dowling is writing on basically that how to build machine learning systems. And one of the chapters is especially focused on this type of feature computations in a streaming manner. Additionally, if you have any other questions or comments, or you want to talk a little bit about this topic, feel free to join our public Slack as well, and we will be happy to continue the conversation there. And otherwise, I hope to see you in the next webinar with us. And thank you very much for your attention.